3.39. Big lap. That's 15-inch straight or 3.39, right?
Yep.
Go ahead.
D equals 3AX.
What?
D as in field.
Sorry. 3AX.
Yeah. Plus 2XY AY. Plus 8x squared y cubed.
8x squared y cubed.
Yep.
AZ.
Yep.
Hang on. And they want what, the charge density or the flux or something?
Charge density and flux.
Okay. So let me take charge density first. Now this is
They
something.
want at a specific point.
We'll get it in a second. It doesn't matter what point, but I wanted to show you this. Remember I said that the integral of d dot ds over an enclosed surface was the charge enclosed. Does everybody recall that? What law is that, anyone? Gauss, my man, my hero, Gauss. That's called the integral form of Gauss's law. The differential form is divergence of d is rho v. That's the differential form of Gauss's law. Now, I didn't cover going over differential or the divergence. But if you have a book, and I hope everybody gets a book, if you look at the back cover of the book, inside cover, you're going to see 4 vector identities. One of them, the first one is called divergence, and it's given in Cartesian, rectangular, and spherical coordinates. The next one in here is the gradient. Think of the gradient as a directional derivative, that's all it is. The third is called the curl. You all see it? And the fourth is the Laplacian. The Laplacian is a second order derivative. The one he has there is only for the scalar Laplacian. I'll talk about the vector Laplacian in a bit. I mean, not right now, but it's going to come up. And these are all very important operators. Now, how many have had the gradient before? How many have had curl before? Just being honest. How many have had the divergence? Divergence, that's the first one. Divergence is a scalar, by the way. How many have had Laplacian? That's the second order derivative. No? Okay. We're going to go through. If you get vector calculus to do all these, and I don't think you had vector calculus. You used to, but it was taken away. So to get this, rho v, which they're asking for, the only thing we have to do is take a divergence of that. What coordinate system are we in, class?
Cartesian.
Cartesian. So divergence, we can put them in all the coordinate systems, but divergence in Cartesian is d dx of d of x plus d dy of dy plus d dz of dz. That's all it is. And we can put it for spherical or cylindrical and spherical there in the back, right? They do the same operation. It's a bunch of derivatives for the coordinates. So for this one, what's the derivative of the d? This is d of x, by the way, in case you don't know. This is d of y, and this is, sorry, circle up. This is d of z. You all follow me? It's just the coefficients of x, y, and z. Correct, class? So what's the derivative of 0, right? Derivative of a constant is 0. You'd be surprised how many put 3 down. It must be 3. Just feels right. No, you gotta know what you're doing. Everybody follow me on this? Don't ever get into that silly reasoning. Well, it must be this. You gotta deductively know what it is. So what's the derivative of that with respect to y?
2x.
2x, that's right. And finally, this with respect to z?
0.
It's 0. All right, so it's 2x. Now, where do they want this rho v at?
1, 1, 1. So
1, 1, 1. Obviously, what? Y and z have nothing to do with this, correct, class? Mm-hmm. It's just 2 times 1 or 2, and it should be coulombs per meter cubed if it's a density. All right, what's the next part?
Okay, find the total flux through the surface of a cube with the side length x from 0 to.
All right, let me draw the cube. So this is x, this is y, this is z. What are the sides?
It's just a length of 2.
Huh?
It goes. It just
0 to 2?
Yeah, 0 to 2.
On all of them. Is that right?
Yeah, I would guess. Yeah, it's 0 to 2 on all of them.
All right, so it's this basic thing. Okay, so it's 2 by 2 by 2. Now, two ways to do it, and I want you to understand this. One is, we can do this. We could integrate d dot ds over the surfaces. Y'all follow me in that? And we could do it. That'll take a lot longer. There's 6 surfaces. Generally, it'll take. Or, we could simply take divergence of d, which we have here, which is 2x, and integrate it over the volume. Do y'all agree with that? Y'all agree? So I'm going to do, because he's asking for the integral of d dot ds, right? That's just Q enclosed. Y'all with me? So you can do it either way. I'm going to start with the divergence. So if I want to find the charge enclosed in this, it would be a triple integral because it's a volume. All the variables would be from 0 to 2, 0 to 2, 0 to 2. Those are from 0 to x, 0 to y. The limits of x, y, and z. Y'all with me? Then I put in the divergence, which is 2x, then the differential volume, right? What is the differential volume in spherical coordinates? I hope y'all did this one.
It's just spherical? Or just
I mean, in Cartesian.
Just dx, dy, dz.
Thank you. Dx, dy, dz. Now, I'm going to go ahead and do the first integral. 2x dx, or x integrated, 2x dx integrated is what? X squared evaluated from 0 to 2. Do you agree with that? I'm going to leave it as x squared evaluated from 0 to 2. Then you got to integrate dy. There's nothing that varies with y, so it's going to be y from 0 to 2 is 2. Then you got to integrate z from 0 to 2, which is 2 as well. So now when you do this, what do you see this is? This is going to be 2 squared, or it's going to be 4 times 4, it'll be 16 coulombs. Do y'all see that, class? The only thing I've done is literally just got the divergence and I did the integration. And Wentworth's problems are just meant to reinforce theory. It's very simple problems. There's nothing hard on this. What if we did it around the surfaces, class? If we took the integral of d dot ds around all the surfaces. Well, what would you have? So if you did this, let's start here. Let's just take this surface right here. That's at x equals 2, right? The differential surface vector ds would be equal to dz dy. Okay, let me get this one. The differential surface vector there would be what? ds, its variation is dz dy, right? And it's in what direction? Ax, right? That's going to be this front surface. So if you do this, if we just start doing this, this would be the first part of the integration. Integral of this, you'll notice it's ax, so you only worry about the ax component here, because you're going to dot them, right? When you take ds dot d, only the ax variables right there would give you a non-zero dot product. Y'all follow me in this class? So it's just going to be 3, and this is a double integral, and then you're going to have dz, I should put dz dy here. So it's going to be dz dy, and this is 0 to 2, 0 to 2, so that's just going to be what? 3 times 2 squared plus, y'all follow me on how I'm doing it? Now you'd have to do this for 6 surfaces, all right? If you do the tops, or the back surface, the back surface is x equals 0, correct, class? At x equals 0, it's still going to have a unit vector, this back surface of minus ax, right? But when you do the dot product here, I'm going to have 3, right? Y'all hear me? But it's got a minus sense to it, right? Minus, y'all follow me?
Yeah.
Have a minus. It'll have plus, and it's going to be, I just block this, minus, same thing as this, 0 to 2, 0 to 2 of 3 dx, dy, dz. It doesn't matter the order. These two will cancel. Y'all follow me on that? Now, the top and bottom. The top, let's go to the bottom. The bottom here is y equals 0. Do you agree, class? And the unit vector for the bottom surface, what would ds be? Class? Bottom.
dx dy.
dx, dy.
That's right.
Is a minus z.
Right,
Yeah.
minus dx dy in the az, minus az direction, correct? I put the minus sign there. You all agree with that? just take a look at this. So take the AZ vector, right? We go ahead, we dot, because it's going to be dotted with that, then we have dx dy over x and y from 0 to 2. We're going to get a variable there, right? Do you all agree with that? Now just follow me on this. Now go up to the top. Now the vector is positive AZ, correct? Still dx dy. When I dot product that, I get the same exact value, only positive. And when I do the integration, they'll cancel. Do y'all see that? Finally, the one you have to worry about is going to be the surface, right? Right, this surface and this surface. Y'all with me? There, the differential vector is either ay or minus ay, right? Now, take a look at this surface right here. The ds is going to be what? It will be minus ay, correct? And it will be dz dx, right? And this one's going to be positive ay, right? But let's talk about that one first. So when I dot this thing within ay, I get this, right? But what is the value of y at this surface?
0.
0, correct, class? So 0 integrated is going to give me 0 on that surface. The only surface that's going to contribute anything is this one, and the differential surface for that is going to be positive ay, right? And it's going to be dz dx, right? Now do the dot product. That's this, right? 2xy, then I got to integrate dx. I get x squared over 2, right? So it's going to be x squared. And then when I integrate y, I get y squared over 2, right? So I'm going to get...
Wait,
Do you integrate?
you're integrating over z.
You don't integrate y there, do you?
Yeah, you integrate
I'm
over
sorry.
z.
I'm sorry about that. You're right. I'm going through this kind of fast. That's where you're going to get all the value. Y'all follow me?
Okay.
We'll do this one. I'll do the final one right here. Yes. So when I integrate this right here, I'm going to have, for the final part for Q, I'm going to have, it's positive A1, so I get 2x, y, dx, right? And it's going to be dz, correct? From 0 to 2, 0 to 2. When I look at this, this is at y equals 2, correct?
Yes.
So I'm just going to put in y equals 2 here, makes this 4, right? Now when I integrate that dx, this is going to be cute. When I integrate that dx, I get x squared over 2, or 2x, from 0 to 2, so it's 2 times 2 squared, right? And then from dz from 0 to 2 is 2, it's going to be 16. It's the same as that. Yeah.
So if it asks for the flux,
That's the flux.
Yeah, that's the
The flux is, let me just say this, because this is a good point that maybe I didn't bring out last time. Whenever they're talking about flux, it means it's an integration of some vector field density over a surface. So when you talk about flux in general, the symbol that we use is psi. It's electric flux. And that's integral of d dot ds over a given surface. This is not a closed integral generally. So when you integrate d dot ds, that's the flux. Now if it's over a closed surface, then it's the charge enclosed. It's the integral of d dot ds over a closed surface. It means it's completely encases everything inside of it. A closed surface is like everything inside of it. The eggshell would be a closed surface. It would be a polar spheroid, a sphere, a rectangle, a square, anything like that where it's closed. There's no way to get flux in and out without penetrating that surface. The flux is really a field quantity. It's really the integral of, think about it, flux D is coulombs per meter squared. Just think about this. When you integrate that over a surface, you get coulombs. Y'all with me? If you take that over a closed surface, it's the amount of charge enclosed. That's all it is. But you can do flux integrations for, when they talk about like mass density they call it mass density flow rate. It's the amount of mass per centimeter or meters squared in a certain direction. If you want the total mass flowing through a surface per second usually, then you'd integrate it over an actual surface area. You've done some fluid mechanics, haven't you, or some stuff and you've done mass density, velocity times mass type, yeah. That's all it is. And you'll get a lot of that later. But you all follow me on this one? That's all it is. Did you have another question about this one?
Your question?
But y'all follow me on this one? It's a straightforward method. You had this in physics, by the way. You should have had it in physics. I think. Everybody with me? Another one?
I do have another one if you want.
What?
If you want another one. 3.41.
Yeah.
This might be similar to this one.
Yeah, it's just the same thing.
Yeah,
It's with,
it is
it's
just
with
the same
spherical.
thing, but with different.
It's with
What is
spherical.
it?
It's a sphere.
Good. We'll do it. Spheres are usually easier. Not always, usually. Depends what
It's
they
just the
want.
same thing, but you have to add
Yeah,
R squared sine theta.
Yeah.
What's that?
But you put it in the right places.
I said it's the same thing, but you need the R squared sine theta, because it's like the
For the differential volume?
Yeah.
Yeah.
Um,
For the divergence. For the.
Oh, yeah, for the divergence, it's going to be 1 over r squared, and it's ddr of r times. Take a look for that.
Oh, yeah, the
I mean, it's
divergence
gonna-
is different.
Isn't it 1 over r and then 1 over r sine theta? I don't
If you
know.
You gotta
look,
use
just
that
look in the
too.
back of the book, third one. It's 1 over r squared ddr of r squared a of r. See
Oh.
that?
Yeah, it's one of these.
Can you see?
Yeah.
No. This is divergence, right? Great. Here. Right here.
Oh, I know. I see. Yeah. I saw it. Yeah.
It should be r squared. Yeah. All right. Anyway, what's the problem? Might as well do it since you're talking about it.
I got a question. Are we gonna have to memorize all the stuff in the back, or are we gonna like be given
Those
stuff like that?
formulas, I
Are they
won't give
like-
you I won't give you Cartesian stuff, but
That's like-
I'll give you the
Okay, that's fine.
divergence and I'll give you divergence, curl, gradient, and Laplacian for cylindrical and spherical. But the rest, if you look at the Cartesian ones,
Well, yeah, the Cartesian ones is pretty simple. I was
Yeah,
talking about
sure.
the other ones.
Yeah.
It's like they're kind of hard to remember.
well, those are things you get familiar with by use. But
Yeah, okay.
what was the problem again?
Okay. D is r squared sine theta
Hold on. D equals r squared. Go ahead.
sine theta ar plus sine theta cosine phi
Sine theta cosine phi.
a phi.
One more.
No,
That's
that's it actually.
All right, good. There's nothing that varies with theta. That is phi, right? A phi? Okay.
Yeah.
All right, what is divergence in spherical? You just did it. It's 1 over, I'm going to put it down, r squared ddr, right? What? R squared d of r, correct? Plus what? 1 over, go ahead. Let's go say it. 1 over r, what?
Sine theta
Sine theta times d
d theta.
theta of,
This would be
just look at the book.
sine theta.
In here?
Yeah.
He
Times
does
the,
that one?
C.
Yeah, a theta sine.
Yeah.
Never. Sine theta, d theta, right? Plus, and then it's going to be 1 over r d phi. And he's going to have, for this one, I actually forgot the form.
It's 1 over r sine theta, and then it's d
R sine, my bad. Okay.
d a d it'd be a d theta. That or d.
D
Sorry,
theta.
d.
Yeah.
No, wrong. It's d phi. That's what I meant to say. My
This
bad.
is phi, right?
Yeah. You
This
said
is-
d theta. Yeah, that's good.
This is phi. That's phi, right?
Yeah.
There's always a 1 over r sine theta. Sine theta. Yeah, okay. I'll go with that. All right. So divergence of d. Let's just do it. So I have 1 over r squared, and then we have DDR of this. R squared times d of r. This is d of r, right, class? So r squared times d of r is what? R to the 4th, right? 4th times sine of theta plus, we don't have a d phi, do we? Or d theta. There is no a theta, right? Isn't that the problem? It's just a
There's no A
phi?
theta yet.
Huh?
There's no A theta
Okay,
yet.
so we don't even worry about that. What about the last one? Plus 1 over r times the sine of theta. And then it's d phi of that. And I think you got this. Sine theta, he just made it awkward. Times cosine of sine theta times cosine of phi. Right. Okay, might as well do it. This is the charge density. So I can see that if I take the sine theta right here comes out in front, so I have sine theta out in front. I have DDR of r to the 4th is going to be 4r cubed divided by r squared is 4r, right? And then plus, and this is 1 over r sine of theta. And dd phi of that, well, the sine theta comes out in front, right? The sine theta is not a function of phi. Derivative of a cosine is going to be what? Minus the sine of phi, class? With me? All right, and you can see these signs cancel, thankfully. So now I have that expression, sine of theta times 4r over minus sine of phi divided by r. What is the position he wants us evaluated at?
1, then
R equal 1?
yeah, R is 1. 45 degrees, so pi over 4.
So this is going to be 4 times 1 times the sine of 45 degrees, right? Plus 1 over 1 is 1, and this is going to be minus the sine. Is phi 45 as well?
No.
90?
90.
Yeah, phi is
90 degrees?
Yeah.
Okay. So that's going to be, pick it up here, we got rho v is 45 degrees is 1 over, is going to be, 1 over the square root of 2, so I have 4 over the square root of 2 minus sine, well, sine of 90 is going to be 1, so it's minus 1, and that's going to be 4 minus square root of 2 over 2, whatever that is. Over square root of 2. Somebody can tell.
Yeah.
What is it? I don't know. But you all see, it's just taking the derivatives correctly. That's all it is. And I would make sure I let you know. You okay with that?
Yeah.
Did you have another problem or no? The one, I mean, I asked you stuff where you had cylindrical charge densities, right?
Yeah.
Flux. I think we should do at least one of those, because some of those get a little
I
confusing.
want to do 335 because I didn't understand the second part of that. 335.
That's a spherical charge.
Yeah, that's what I was just talking about.
We'll do it.
He said cylindrical. I thought.
What's that?
Oh, did you want to do cylindrical?
Spherical's fine. Spherical or cylindrical, they're the same concept. I want to do something where we have an integration over a region, spherical or cylindrical, where we have to calculate the defect, and we can exploit symmetry. I think it's a defect. All right. Okay. Boy. So now let's see. This week we got a full week, right?
Mm-hmm.
Yeah.
And then following week, Monday's off?
Yeah,
Something
I
like that.
think.
I think it's Monday. Fine with me. All these holidays.
I'm pretty sure we also have Friday off too.
This Friday?
For next Friday, for mini-mester exams.
Yeah, so you get one day that week to go.
Yeah, so we have today, Wednesday, Friday, and then next Wednesday, and then the Wednesday after that is the test.
Yeah, don't we get that Monday off too?
Which one?
We get the next.
Yeah,
two
we also
Mondays
get
off,
that
right?
Monday off.
For
Yeah,
what?
yeah.
I have no idea.
So we have this class plus 2 more. Then next
Well,
Wednesday.
why do we get the following Monday off?
For
Juneteenth?
also mini-mester. So Juneteenth, the week after, is for mini-mester finals.
Friday and Monday?
And Thursday, but I guess that doesn't matter.
Whoever's doing the calendars.
Yeah, I don't know. We have a lot of days off after this week.
Yeah.
Summer is chock full of stuff, man. I don't know who's, well, I shouldn't complain. Let me take a look what they actually are doing. Because you can get killed with the amount of material. If you don't have classes, you can be like, ugh. All right. So, for this one, go ahead.
I got
39, you say? Or what?
335.
335.
35.
Go ahead.
Okay, it says a spherical charge density is given by rho v equals rho a times r divided by a.
This is equal to rho, all right, rho 0.
Or rho, yeah.
Rho naught, and what is it, times?
Times r divided by a. All of it over A.
Okay, I got it.
And then that's from
Coulombs per
zero,
meter cubed?
I guess. It says from 0 to r to a.
All right. So here's,
This has no units.
okay, well,
Yeah.
it's, rho naught will have units. All right, this is from 0 to A, right?
This is the
From
one where it
0
wants to
greater
sit.
than R, less than A? and-
Yeah.
Okay, go ahead. And
And
0
then
else?
it's 0 for everything else, yeah.
Yes. Go ahead.
It just wants you to derive equations for the electric flux for all of R.
You want D. They want D inside and outside the sphere. It's smart until you get real familiar with this to draw, sketch something, sketch the picture. What you have is something that's a spherical coordinate system, and it's just a ball of charge limited by radius A. Inside it, you have rho v equal to this. Outside of it, 0. Now, what I'm about to show you, this holds for cylindrical coordinates as well as this, but it's real important to see it. First, you all agree that there's a high degree of symmetry. It is spherically symmetric. Doesn't matter what way you look at this thing, it looks the same spherically. It doesn't matter how you rotate it. So we go to 2 regions here. The first region will be for the actual R value less than or equal to A, greater than 0, or equal to 0. So here we construct a little Gaussian surface. And I'm going to blow that up. So if I think this is A right here, now I'm going to come out with a surface R that's going to be less than that. This is my Gaussian surface. It's imaginary. So from here to here, I'm going to say the integral, that's a surface, it will be integral of d dot ds over that surface that's inside there is equal to the integral, triple integral of rho v dv. Y'all with me on this one? Now, it's spherically symmetric. You could write out, and don't do this, but you could write out this part of the integral. You could say what that really is a double integral of the d field. Now, d is going to be constant at that distance of dr right here as a function of r, ar, times the differential surface element in spherical coordinates. Differential surface in spherical coordinates is r squared sine of theta, d theta, d phi in the AR direction. Y'all with me? That's the outer circle, differential spherical surface. If you're in spherical coordinates and you're talking about holding R constant. Y'all agree with that? It's dotted into that, it's in the AR direction. Now, if you look at this, theta will go from 0 to pi, and phi will go from 0 to 2 pi. We're only going to do this once, we won't have to do it again. Y'all with me? What that really is just d of r, that value, times the surface area of a sphere, which is 4 pi r squared. That's all this will be. When you do the dot product and do the integration, you find d of r comes out in front, right here. And now, you get ar dot ar is 1. Then I integrate sine theta d theta, and r squared comes out in front too, because there is no dr term. When you have sine theta d theta, integrate, that's minus cosine of theta, correct? You all with me on this? Cosine, minus cosine of theta from 0 to pi. Well, I can switch it and make it from pi to 0. Cosine of 0 is 1. Minus cosine of pi is minus 1. So 1 minus a minus 1 is 2. So it's times 2. Now when you integrate phi from 0 to 2 pi, you integrate phi, you get d phi, you get phi, evaluated from 0 to 2 pi is just 2 pi. And you see that what this is nothing more than 4 pi r squared times d of r. So it's really the surface area of a sphere is 4 pi r squared. It's that times d of r. That's all it is for the integral of d dot ds. How many saw that before? You got it with. I wanted to do it one time. So this part is always, for spherically symmetric system, going to be 4 pi r squared dr of r. Over here, now you got to find the integral of rho v over the differential volume. I'm going to do that here, so we'll just call that q. And if we do this, we have a triple integral. This would be q, and this is for, again, r less than or equal to a greater than 0. The triple integrals start with the density, which is rho 0 r. And that's r over a. And then it's the differential surface, or differential volume. Now the differential volume is going to be r squared times sine of theta. Then you're going to have d theta, d phi, dr. I'm putting all the variables. You got to go dr, right? Everybody with me? Okay, for this one, theta goes from 0 to 2 pi, or 0 to pi, pardon me. Phi goes from 0 to 2 pi, and r goes from 0 to r. And technically what I should do, you all remember doing this in calculus, anytime you have something where the limits have a symbol that are part of the kernel of integration, you got to prime the inner coordinates. Do you all remember that? How many remember that you can't integrate like the integral from x dx from 0 to x? It has to be x prime inside, just because it's they call it a dummy variable. When you integrate, it goes away. It's a symbol, that's all it is. So when you do this, what do you get? Now, I already did the first part, but you all see how the rho 0 and a can come out in front, right? Mm-hmm. So rho 0 over a can come out in front. Now, when you integrate d theta sine theta right here, you're going to get minus cosine theta. From 0 to 2 pi is going to give you a 2. Do you all agree with that? Now when you integrate d phi from 0 to 2 pi, what do I get? D phi integrated is phi. There's nothing, it's a function of phi in there. From 0 to 2 pi is just 2 pi. You can see those two just go into 4 pi, right? 4 pi. Now, when you do the dr integration, I got r squared times r to the first power, right? Yeah. So that's going to be r cubed. Do you agree with that, class? Right? R squared times r is r cubed. When you integrate r cubed, you get r to the 4th over 4, correct? Mm-hmm. And so this is going to be r to the 4th over 4, and that's the charge inside. Now I can neaten this up so that's going to be, I got 4 pi over 4 is pi, it's really rho naught over a, and then it's going to be pi times r to the 4th. That's that integral is equal to this, 4 pi r squared. That's a good problem. Is equal to 4 pi r squared. And it's times d of r. Now this is for r inside. And y'all can see, just by manipulating this a little, the pi's cancel, right? The r squared and r to the 4th go, so I have d of r here. I put it, for this particular case, d of r is equal to, and if you look at this, it's going to be, we divide by pi, right? Divide by 4, get all this stuff, and I end up getting, and r squared gives me r, so I have a rho naught over 4a r to the r squared. So this is rho naught over a, and it's going to be over r squared over 4. And this would be for r less than or equal to a. And you could say greater than or equal to 0, but it's applied. Y'all agree? What's the next part? This is when people mess up, by the way, because you said you didn't get it. I want to make sure you get it.
Wait, where's your final answer for this part? Right there.
Take a good look. Take a moment. Just confirm it.
Gotcha, cool. That's what.
Just make sure you see it.
Yeah, that part makes sense.
Here's the part people mess up. I'm going to do it over here. And I'll tell you why. It's the integral of the charge that mess up. Now, for this part, now we're going to have r greater than a. So you're outside the spherical surface where the charge is. It's still the integral of d dot ds over the closed surface is equal to the integral of rho v dv over the volume. I put it down generally, right? We know this is just going to be 4 pi r squared d of r. You all with me? It's just the surface area of the sphere times the value of d. So this will always be 4 pi r squared times d of r. That's always going to be the case. Now over here, the difference is now it doesn't go from 0 to r, it goes from 0 to a. Because remember, all the charge is limited to a. Charge density. With me on that?
Oh, yeah, that makes sense.
All right, so now you come over here, and I'll write this down one time. So here, it's going to be rho v, and you had rho v is, what was it, rho naught over a times r, right? Is that right?
Mm-hmm.
And then the differential
Yeah.
volume is r squared times really sine of theta d phi dr. This is a triple integral. Theta goes from 0 to pi, phi goes from 0 to 2 pi, and r goes from 0 to a. That doesn't go to r now, just goes to
So it goes from 0 to a because it's the r that's outside of the.
Well, think
and
about the
charge
density.
can only go up to a, so it's the
charge
outside.
density is 0 beyond that, right?
Mm-hmm.
We could write 0 integrated to a, but 0 times anything is 0. So the charge you have to worry about is from 0 to a. That's the only place that charge density is non-zero. That's it. So when you do this, take a look at what you get. On this side, you still have 4 pi r squared d of r. Always will. Over here, all right, we'll do it this way. What's the integral of sine theta d theta? Minus cosine theta from 0 to pi is going to be 2. With me on this? I do this too often. Phi integration is 2 pi. So I got 4 pi. The theta and phi integration give me 4 pi unless there's another function in here that varies with theta or phi, and there isn't. So I have 4 pi, guaranteed. Now I've got to account for rho naught over a, those are constants. Now I have r cubed integrated. That's r to the 4th over 4, correct class? From 0 to a is really a to the 4th over 4. Bless you.
Thank you.
Or if it wasn't sneezing,
Yeah.
whatever, stay healthy. Y'all with me, class? Now, can you all see, the only thing I'm going to do is cancel that, cancel that. I have a comment here that's important. Now, I come over here, I can whack that down, make it cubed, right? And then you can see what I have is really rho naught over 4 here, and then I have a cubed divided by r squared. And that should be the value. Is it, class?
Yeah.
Y'all with me? That's all I'm doing is just methodically going through it. I'm a little sloppy here, but I hope you appreciate it. You with me?
Yeah, that makes sense.
Okay. You asked me, Chase, about earlier today about what happens if you have a line charge density and point charge and you want to find the electric field at 0. Since he asked me, I'm just going to do this real. These are kind of neat. They're just thought-provoking. If you understand the principles of what's going on, they're not really hard. What problem was that, Chase?
I believe it was 3.15.
So,
43. I'm sorry.
3.1?
What? Yeah.
That's a line charge and point
What is
charge.
it? 3.15?
Yes, sir.
All right, so as I recall, here's X, here's Y, here's Z, and you have a line charge density at
Wait,
X.
what?
Take it?
Wait, your
Z.
Y and Z are the same axis.
Your C's
X.
echo as well.
It's supposed to be Z here. My bad. You get me, I hope you get me, right? All right, if for this one, get done exercising, I haven't eaten today, but I'm making. I'm gonna have to change the amount of activity before these lectures that I'm gonna eat. All right, everybody with me on this? It says the charge density is and it's gonna say 0, -2, 0. That's the coordinate where it pierces that point, but it's in the x direction. Y'all with me, class? It'll just give you, it's on the x-axis, and it's going to pierce the point 0, x is, I think it's 0, -2, 0. Is that right? Or is it just, what is it?
It just says X is 0, Y is -2.
That's it. That's this point right here. So it's up in, x is 0?
Yep.
Yeah.
That ain't the right, this ain't right.
Oh, that's it?
Huh?
That's the way he's got it.
No, but hold it. X
It
is
says
0.
X. I'm reading it. It says X is 0.
X is 0.
Maybe it means
here.
Oh.
Yeah,
Yeah.
that's here. That's in a. I
I
mean,
think it's the same thing, but on Y. It's just that.
read
way.
that problem, could you? Hold on.
A line charge with charge density 2 nanoscoulombs per meter exists at Y equals -2, X equals 0.
Oh, y equals -2 is here.
Yeah, X equals 0.
All right, go ahead. What direction? Z direction?
It does not give one, but
There
I
has
guess
to
that
be Z.
it has to be, right? Yeah.
Has to be Z, right?
Yep.
We had the wrong contours, but it got the. So this is the charge. It goes up and down the Z-axis, and this is rho L. And then a charge exists, or where to put a charge.
We put a charge to make the E field at the center 0, at the origin 0.
All right, so you're going to have on the y-axis, right?
Yeah.
And what's the charge? Is it 8 nanocoulombs?
It is, yes.
All right, and this is
2 nanocoulomb per meter.
Rho L is 2 nanocoulombs per meter. It's a good problem. Now, the reason is this. It forces you to think. It doesn't, you're used to doing forward problems or just solving for fields when you got different charges. Here, it says they give you the field, they want to know where the charge is that causes it. Same amount of variation, only the order is different. So here, if I have a line charge up and down the z-axis at y equals -2, the electric field from the line charge at 0, right there, or at x equals 0, is going to be, first it's going to be in the positive y direction. It'll be rho L over 2 pi epsilon naught divided by that distance, which happens to be true 2, and it will be in the AY direction. Now, I don't want to make light of this, and I'm not trying to zoom through it, but you ever also, you got charge density of the z-axis. It's exactly 2 units, 2 meters, away from the origin, but it pierces the y-axis. Y'all with me? Mm-hmm. And here, for that one, if you look at that, that has to give me a positive field at the origin. It has to be in a positive y direction. The electric field's going to point radially away and be in the positive y direction. Do y'all agree with that? Now, where do I put a charge so the field is 0? Well, first the field from a charge up here at any point y, that's at a point y way, the electric field from that point charge at 0, and I'll just call it a Q, will be equal to, it'll be in the minus direction going that way, and it's going to be minus Q, whatever Q is, divided by, and I can put it as 4 pi epsilon naught instead of K, and then it's divided by this distance, which is just going to be y squared in the AY direction. The sum of those two have to be 0 at the origin. That's written for the origin. Do you all agree with that? So if you just equate them, this would have, if you have E rho L plus EQ equals 0 at the origin, that means that this is equal to that. And that means that rho L over 4 pi epsilon naught, because it's 2 times 2 is 4 pi, is equal to Q over 4 pi epsilon naught y squared. Do you agree with me? Just writing it down. I think you all see this. Somebody tried that one, but this is a good problem because you got to visualize this, and it becomes very trivial after you see these things. You all see that the 4 pi epsilon naught cancel on both sides?
Yep.
Doesn't matter. So now I can see that y squared is equal to q over rho L, or y is equal to simply the square root of q over rho L. And I think q was 8. They're both nanocoulomb per something. Rho L is 2, so square root of 4 is 2, and I think that is the answer. We did this one. Is that right?
Yeah, it's gonna be 2.
Is that right?
I don't know.
Yeah, and
Yeah.
the reason I'm saying I'm doing this is because those are things, we don't do problems, usually they just want the electric field at a point, they don't want the position of the charge that causes a given electric field. But either way, forward or reverse, inverse operation, you need to be able to see and do. Okay? My sentiments exactly. You know, one thing I noticed differently, during COVID, I can't tell you how many people had beards. I mean, now you didn't shave today, but I mean, I'm not seeing beards. I mean, do you remember COVID? When I had to teach COVID, I mean, you wouldn't believe how many students and professors.
People would just show up to class looking homeless.
I'm telling you, the professors too. I was bad about it. And if I teach from home, hey man, I ain't gonna dress
I
up.
can't grow a beard, so.
Huh?
So I can't grow a beard. Well, I can grow something that looks like something, but it's
What?
not
I don't
uniform.
like beards.
Just itches, man.
I had a beard only one time in my life. Was for a reason. I was at Penn State and I tore my Achilles tendon. I was a grad student. So I'm in a cast for 10 weeks, like this. And I have to hobble in the wintertime at Penn State, where you get snow and the wind gets bad. And I did about 1 mile, 1.5 miles, one way, 1.5 miles back, with crutches and books. And I freeze. So I decided that, and I grew a beard. Now the bad thing about long beards, especially food gets stuck and it itches, and it's just, for me it wasn't that cool. As soon as that foot got better, it came off. But that was my experience with beards. Now if I go hunting, something like that, I gotta be out. If I gotta be outside for any extended period in cold weather, I'll grow a beard. But that's about it. I don't know if anybody else has similar feelings. But some people just like beards. They think they look better. I don't feel like it. Okay, we did divergence in Gauss's law. We did the point form. And the next thing we're going to do is something that's probably going to make your life easy. It's the electric potential voltage. Now this is something you've had. Anybody remember the biggest reason why the electric potential, the voltage, was so much better to calculate and easier to calculate than the electric field? Anybody? Well, it's a scalar quantity. Electric fields are vector quantities, right? So, I don't know if you remember this from physics. I could go through a whole 9 yards, and I think I'll go through a little of it. But in general, you talk about force, and you talk about the integral of force to find the energy or work done. So, if you have a charge Q, and it's at a point A right here, and there's an electric field. I'm trying to just be real casual about this, but you've got an electric field, and you've got a charge Q. Right here. There's a force acting on that. The force acting on that charge is Q times E. You all remember this? Right? Now, if you think about the field, just like you think about gravity being a field, if I take a mass here and I let it go, it'll come down and hit the floor. The amount of work or energy that the field does would be the integral of the force pulling down integrated over the distance. There's not much change from gravity at this point versus that point. So it just be the force acting on that, which is mass times acceleration, whatever the mass is, times 9.8 meters per second squared, times the distance. You with me? That would be the work that the actual field does. If I took, and this is important to see this, if I grabbed that thing and I took it from there to there, gravity would, in a sense, do negative work. The amount of work would be opposite, right? I would actually add potential energy to this. Do y'all follow me in this class? I would do work. So I'm the external force. I would be doing positive work. Just get that down. Gravity pulls down, goes from here to there, gravity does work. If it goes from here to here, I do work, gravity does technically negative work. So if I integrate the integral of QE, which is the force, dot dl, from A to B, that's positive work for the field. And that would be equal to Q times the integral of E dot dl from A to B. And we'll call that's the work that the field does. Now, the work that you would do if you took it from point A to B and you went in the opposite direction would be the work an external force does. Does that make sense to everybody? So you could say that the integral of Q from A to B of E dot dl in the opposite direction, this would be the work that an external force does. And I'm trying to be clear about why we call it a voltage in a second. Now, if you forget about the value of the charge right here, in other words, if we normalize the amount of work for any charge, we're trying to normalize the work by the charge, that's called the voltage. This is voltage. And it's the voltage from point B minus voltage point A. And I'm going to show you where this is in the book. Little calculations, you've done it. So this is 367 is where I'm trying to show you the AB concept and how you get this. This is the work the external force does. And then on page 168, equation 3.68, it shows you the voltage difference, VBA. And this is usually labeled as VBA. Now, you all remember seeing something like this back in the day when you had physics? Right? It's real important you understand this is the work, or this is the voltage associated with an external force moving something. So a positive voltage relative to a negative voltage means if you put a charge there and the field could move it, it would move from the plus to the negative. That's an important concept you should get out of this. So that's the voltage. Voltage is nothing more. V, call it VB minus VA, which is VBA, is nothing more than a negative integral from A to B of the E field dot dl. That's it. We're going to see a lot of things about this. But you remember this basically from physics. You're going to love voltage because you can get the electric field from it by simply taking a gradient. And that's why it's so nice. While I'm at it, I'm just going to tell you this. I'm not going to prove the whole thing. But now that's a differential, this is an integral form of the relationship of voltage to electric field. You all follow me in this? Remember, we had the integral form of Gauss's law. The integral of B dot ds was charge inside, right? Here's the differential form. The E field itself can be gotten by taking minus the gradient of the voltage. Now the E field's a vector. And here's what's really beautiful. Y'all with me on this? This is called the gradient operator. It's a vector operator. It's easy. Now here's the thing. If you have something where you calculate the voltage and you leave the voltage in terms of the coordinates, x, y, z, or rho, theta, z, or whatever, rho, phi, z, whatever, and then you take the gradient and you get the E field with only doing one integration. And you'll see more of this later. It's much easier to get the voltage and do a gradient than do all the vector integrations based on charge density and get the components of the E field. Just telling you, it is numerically and usually analytically much easier. So there's one other thing in the book that, well, this is on page 169, what we're going to talk about, and there's a couple things. Now, you know what a conservative field is, people? You guys remember the term conservative field?
Yes.
What does it mean to you? You remember? There's one essential thing. Gravity is a conservative field. It means if I start at a point, let's talk about gravity for a second. If If I start at this point, I'll take a look at the amount of work I do, and I move that thing upward, and I let it come back down to its resting place. How much work did I do?
That's 0.
0. What if I take it, move it this way, up, over, and back? How much?
0.
What if I move it down, over, wiggle it, move it up, move it, same point I started? How much? 0. 0 work that I do and the field does, even though it's not quite true, if in fact it's a conservative field. The electric field from a charge is a conservative field. The electric field from an accelerating charge is not. But for statics, this is for statics. Static just means nothing moving. If you take the integral of E dot dl around any closed loop, you get 0. I can multiply it by charge and say the work done, if you go from point A all the way back to point A is 0, but that's true always. It's a conservative field approach, just like with gravity. All right, it always will be. Now, one last thing. I know you're anxious for your quiz, but one last thing. Voltage, does everybody understand that when you read something that says, warning, 10,000 volts, it means nothing unless you know where the 0 is. Now, implied is that the ground, the earth ground is 0, right? But voltage is always between 2 points. Now, a lot of times, and you know this, when I take a look at this equation right here, when I say that VB minus VA right here is equal to the integral of minus from A to B right here, and I'm doing it right from the definition there, E dot dl. Most of the time, you know what a ground is, right? What is an electrical ground to you, in your words? What does it mean?
0 volts.
It means, that's right, that you consider that point to have 0 volts, and everything in the circuit will be measured with respect to that, right? So what they normally do, not always, but they're going to say this: if you have a single charge system, a single charge, and this is always true, you can assume at infinity the voltage is 0. That's guaranteed. We can go through this one a little more time. But usually, if you have any finite amount of charge, almost all problems set the voltage at infinity being 0. Okay? That's just the way it's done. Because technically, when you integrate E dot dl, if you have like a standard amount of charge, Q, you get Q over 4 pi epsilon r squared AR. Then you have to integrate that dot dr. You're going to get something where you're going to get 1 over r values. You all follow me? You're going to 1 over r squared integrated is a 1 over r. Well, 1 over r when r is infinity is 0. You all follow me on that, class? It is. So usually what they'll do is say this is going to be 0 for any finite charge. And then they can say this. If that is the case, and I know I'm throwing a little much at you right here, they can say instead of a differential electric field from a differential charge, that if we assume we have finite charge and infinity is 0, then I can say if I have a little chunk of charge here, call this dq, then if I'm a distance r away from that, there'll be a scalar differential voltage that will just be dq, whatever that q is, over 4 pi epsilon naught r volts per meter, assuming that V as R goes to infinity is 0. Now, that's really nice, and here's why, and then I'll give you a quiz. And I'll give you problems on this one. Please do that. When you look at that right there, you see, remember how we got the electric field by integrating the value of the differential electric field over where the charge density exists, right? When we integrate this over where the charge density exists, we'll get the voltage, but it's a scalar. It's easy to do this. And you'll see that next time. So now I resituate you. How about that row stay there, you over there?